So in the last laboratory about the stable diffusion, so it is designed for us to the transition from the computer vision classification models into generative AI and diffusion models. So discriminative models versus generative models. We previously worked with models such as convolutional neural network, ResNet, GradCom, Silencio maps. These are discriminative models. Their job is from the image we fed to the model, and then we have the class label output. Like we have the cat image and process the convolutional neural network, and then we have um, it, 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 it will predict it as a cat, like that. So the model learns what class does this image belong to. So diffusion models are different. They are generative models. Their job is from text prompt to model to the new image. Example, a puppy riding a skateboard in Times Square. So the model creates an image that never existed before. So stable diffusion pipeline. So in our notebook laboratory, stable diffusion pipeline contains several models um, already connected together from prompt and then tokenizer. After that, we have the clip text encoder. Finally, we have the embeddings, text embeddings, and press the unit denoiser and V decoder. And then to the final image. Next, loading stable diffusion. The node loads the model through load model pipeline. This helper function hides the complexity of loading token loading of the tokenizer, text encoder, scheduler, unit, VAA. Without helpers, loading looks something like we have the stable diffusion pipeline, and then we have too much process for the codes. Next is stable diffusion 2 architecture. In the laboratory, we use especially use this diffusion 2. So the important components is the clip text encoder, converts the red sports car into embeddings. So the model does not understand words, it understands vectors. So the unit is the brain of diffusion. So its input is noisy latent, prompt embedding, and time step. So the output is predicted noise. So we should remember that unit it predicts the noise, not the image. Next, scheduler removes a small amount of noise each step, from 100% noise, 90%, 80%, 70%, and by the 0%. Next is VA decoder. It transforms data representation into RGB image. Next is random seeds. So we use the torch generator and manual seed function. Example, torch generator is equivalent to the torch generator that manual seed, and manual seed is set at 42. It guarantees reproducibility. So it was the same prompt as a castle on the mountain, and same seed 42, and produces exactly the same image every time. So different seed 43 produces different composition, different clouds, different lightning, different castle, but still follows the same prompt. Think of seed as prompt is equivalent to destination, but the seed is starting location, and different starting points reach different versions of the destinations. Okay, so in our first generation, generates image using the pipe prompt.images and index 0. So the workflow is from prompt to random noise to 100 denoising steps, and then we finally have the image, the noise image. Next is num inference steps, means a number of inference steps of how many denoising iterations occur. Example, number of inference step is 20. First generation noise from 10 cleaning steps to image. So the results is faster, less detail, and number of inference step is 100. So the result is sharper image, more detail, slower generation. Think of it like sculpting from 20 steps to rough sculpture, and if it's 100 steps, is polished sculpture. Next, we have a guidance scale. This parameter controls how strongly the model obeys the prompt. Example, if we set the guidance scale is equivalent to 1, the model behaves freely. So if you have the prompt a cat, astronaut, it will result maybe a cat and maybe an astronaut. It has a free will or behaves freely. But if we set the guidance scale of too much or large, like guidance scale 7.5, it is a typical value. The model follows the prompt closely. And if we have the guidance scale of 20, it is increasing, we could act very aggressive. It can create distorted images, oversaturated details, strange artifacts. That's why if you see some artificial intelligence photos over the social media that it's unusual, distorted, or a mix of something different, weird photos or images, it might use the guidance scale of too much. Think of it as teacher giving instructions, and the low guidance is do whatever you want, and high guidance is follow exactly what I said. Next is negative prompt. It introduces negative prompt. Like for example, if it's the negative prompt of blurry, low quality, and extra fingers, so the model actively avoids these features. So positive prompt is beautiful portrait of a woman, negative prompt is blurry, deformed hands, and result is better image quality. Intermediate denouncing steps. This is one of the most important concepts in the laboratory. So it saves intermediate latents during generation. From step 0, it has a pure noise, and then from step 0 to step 10, like for example, the shapes appear, the noise gradually disappearing, and from the step 5 like 25, like for example, we have the face outline appears, and step 50 eyes appear, and step 75 details appear, and finally in the step 100 we have the final image. So in the laboratory, the notebook that we use, it decodes this latents using VA decoder, so we can actually visualize generation process. So this is exactly the concept we asked in the last videos. Latents are the compressed mathematical representation that the model is refining. Text is DDPM, or stands for Denoising Diffusion Probabilistic Model. This is the original diffusion model. From the, like for example, in the forward diffusion, in the training, we have the image, we add the noise, gradually add more noise, and then so on and so forth, and we have the pure Gaussian noise in the end. And then we reverse the diffusion. This is the generation happens. From the noise, we remove the noise, gradually remove it more noise, and repeat it, remove, and then we have the final image. This is the entire idea behind the diffusion models. Next is pixel space versus latent space. So DDPM works in a pixel level. The denoising diffusion probabilistic model directly modifies 512 by 512 by 3 pixels. Is expensive. So diffusion, the stable diffusion works in latent space. So the image first becomes 64 by 64 before latent tensor. Initially we have the 512 by 512 by 3, and then the VA encoder reduces it as 64 by 64 by 4. This is much smaller. So advantages is faster, less virtual RAM, cheaper training, and higher resolution generation. So here's the most important takeaway. The entire stable diffusion generation process is from prompt and to clip text encoder to tags embeddings to random latent noise, and the unit predicts noise. And then we have the scheduler removes noise, repeat many times until we have the clean latent. And then the VA decoder convert it to the latent decompress the RGB, so we will have the final image. So it combines almost everything we have been studying, from the embeddings, attention, transformer, latent, representation, convolutional networks, iterative optimization, generative AI. So we are essentially moving from what is this in this image to create an image that matches this idea. And that's it.